This module focuses on design of FIR type of filters. Before we learn how to design an FIR filter, it's important to understand a few terms. The first terminology that we have is called as frequency response. Let us understand what is frequency response and how it can be measured for FIR filters. Now, frequency response is the response of an LTI system when you apply an input which is a complex exponent. So here the complex exponent is e power of j omega n. When you apply input which is equal to this value, your output y of n will be the same exponent e power of j omega n multiplied by h of e power of j omega, its magnitude. This component is termed as the frequency response. Therefore, your output is the input times the frequency response. We are aware that in the case of an LTI system, the input-output relation is governed by linear convolution. Therefore, y of n is equal to x of n times h of n. It is x of n convolved with h of n. Alternatively, by making use of commutative property, we can express it as h of n star x of n. The formula becomes summation k between minus infinity to plus infinity h of k x of n minus k. Now, since we are considering the input to be a complex exponent, x of n is taken to be e power of j omega n. Now, replacing in place of x of n minus k. Since the index is n minus k, it becomes e power of j omega into n minus k. Now the exponent could be split into two terms and it becomes e power of j omega n into e power of minus j omega k. The term e power of j omega n is independent of k. Hence, it can be taken outside the summation. And what remains is the quantity which is shown here. Now, the quantity shown here is nothing but the magnitude of h of e power of j omega, which is the magnitude of the frequency response. We are aware that the frequency response is a complex value, hence we can easily find its magnitude. Now, the summation here represents the frequency response. Therefore, h of e power of j omega should be equal to summation k between minus infinity to plus infinity h of k e power of minus j omega k. This above equation resembles that of the discrete time Fourier transform. Hence, we can conclude that when the input is h of n, which is impulse response, if you calculate its discrete time Fourier transform, you end up with frequency response. Therefore, the relationship between the impulse response and frequency response is related through the discrete time Fourier transform. Taking the inverse discrete time Fourier transform of h of e power of j omega, we obtain the impulse response. Let us learn a few things about the FIR filter. When you compare IAR, which is infinite impulse response, with FIR, which is finite impulse response, few of the properties will emerge. The first thing is that whenever you design an FIR filter, the order n is always larger compared to that for the same specifications when designed using IAR method. So the IAR results in a smaller order. The IAR exhibits something which is called as nonlinear phase. That means that the magnitude part of the frequency response is reproduced faithfully, but the phase is not exactly reproduced. Now, in applications which are sensitive to the phase, where the phase should be kept intact, then we should go with FIR. Okay, so FIR is characterized by what is called as linear phase. whereas IAR has non-linear phase. We have already discussed the role played by the frequency response. The frequency response is a complex value, hence we can get two plots. One is called as a magnitude plot, the other is called as a phase plot. The magnitude can be typically expressed in terms of dBs by taking 20 log of h of e power of j omega. So, in the case of IAR, it generally reproduces the magnitude faithfully. That means that when you give a particular input, the output will preserve the particular magnitude. But you cannot say the same about phase. Now there are applications like, for example, the phase is conveying the information along with the amplitude, then altering the phase may cause you to misinterpret the result. Therefore, in this case, FIR is preferred. FIR has the drawback of having higher order. That means that the number of stages for FIR will definitely be more. Hence, the computation time will be more and the number of stages will add up to the cost, the time of computation and the complexity. So these are the challenges in the case of FIR. But the tremendous plus point is that it is inherently stable and it also has linear phase. Now, let us look at the system function for FIR. Here we have shown the general system function, where the numerator coefficients are depicted by bk, the denominator coefficients are depicted by ak. Now what we should observe in the case of FIR is that only the first coefficient a0, which is 1, is preserved and the remaining coefficients are made 0. That means that the system function for FIR takes a very simple form as shown here. We have summation k is equal to 0 to n bk z power of minus k. Now if you expand this, the equation will be written as b0 plus b1 z inverse plus b2 z inverse z power of minus 2 and so on till the last term bn z power of minus n. The length of this is definitely finite and it is controlled by the coefficients which is called as bk. Now if we want to change it to the time domain, we have to take the inverse Z transform. So suppose you take the inverse Z transform. So you could possibly express it as h of n. You will obtain what is called as h of n. Or if you prefer to have the difference equation form, you can do it. You have to do substitution of h of z with y of z by x of z. Then you have to cross multiply the terms and then you have to take the inverse Z transform. The difference equation form of the above system function will take the form as shown here. Now we observe from the difference equation that the current value of output is dependent only on the input terms. It is not dependent on the past values of output as it was in the case of IAR. IAR had loops and because of the loops it was said to be unstable. Here, since there is no concept of feedback involved, then the looping is avoided and hence the system is said to be inherently stable. Now coming to the impulse response, when you take the inverse transform of the above equation here, we end up with the equation h of n is equal to b0 delta of n plus b1 delta of n minus 1 plus till the last term bn delta of n minus n. Now what we observe here is the coefficients are b0, b1 and so on, and most definitely we can say that the length of the impulse response is finite. Hence it is called as finite impulse response filter. It is FIR. The length of the impulse response is always. Now to understand the significance of linear phase, let us consider a low pass filter having the frequency response given by hd of omega, which is equal to e power of minus j omega alpha for magnitude of omega which is less than omega naught. Now omega naught is assumed to be certain cutoff frequency. We can talk about that in further topics. When the frequency is between omega naught and pi, then the frequency response is said to be 0. Now frequency response can be written as hd of e power of j omega. Alternatively, as a shorthand notation, we can simply call it as hd of omega. So this informs us that it's a function of omega, which is a frequency. This hd of omega, where d stands for desired, because we are talking about an ideal low pass filter. So hd of omega is periodic with a period which is equal to 2 pi. Therefore, hd of omega plus 2 pi m, where m is an integer, should be same as hd of omega. Now, the magnitude and phase response for this ideal low pass filter is as shown below. The magnitude plot is shown here on the left. The magnitude response shows that between the frequencies 0 to omega naught, the magnitude is equal to 1. This is expected from a low pass filter. And between omega naught to pi, the value is equal to 0. Now, the other side is symmetric. Therefore, between 0 to minus omega naught, we get 1. And between minus omega naught to minus pi, we get 0. Therefore, in the entire duration equals to minus pi to plus pi, we are depicting the behavior of the filter. So, in the case of digital frequency, it is sufficient to consider the frequency between 0 to 2 pi, because we know it is repetitive with a period which is equal to 2 pi. So alternating, you can consider between minus pi to plus pi. The interval is equal to 2 pi here as well. Now coming to the phase part, theta of omega is angle of hd of omega. Here we consider the magnitude, here we are talking about the angle now. Now, the phase response we can see varies linearly in the range between minus omega naught to plus omega naught. So it is linear and it carries a slope which is equal to minus alpha. Now this is what is called as linear slope. In the case of IIR, we probably would not have obtained a linear slope like this. Now between omega naught to pi it is 0, and between minus omega naught to minus pi also it is 0. So in the range of usable frequencies, it is exhibiting a linear slope. So the phase is said to be linear. Now, let x of n be the input and y of n be the output of an ideal low pass filter, which has an impulse response given by hd of n. Now, low pass filter is an example of a linear time invariant system. Therefore, we may be writing y of n is equal to x of n star hd of n, where star is linear convolution. Call this equation as equation number 1. Next, taking the discrete time Fourier transform on both sides, we get y of omega is equal to x of omega into hd of omega. The operation of convolution in the time domain, in the frequency domain, it becomes a multiplication. Next, substituting for hd of omega as we had described from equation A. We had seen that for a low pass filter, the hd of omega is equal to e power of minus j omega alpha. So therefore, we multiply that quantity with x of omega. Then we can say that the output frequency response y of omega is equal to x of omega times e power of minus j omega alpha. For omega magnitude, which is less than omega naught, for omega naught between omega between omega naught to pi, the magnitude is equal to 0. Further, if we take inverse discrete time Fourier transform on both sides of the above equation, we get y of n is equal to x of n minus alpha. Therefore, we can conclude that the output here is simply the input which is delayed slightly by a certain value which is equal to alpha. Therefore, output is a delayed version of the input. It is not going to alter the phase. The magnitude and phase are kept intact, only there's a slight delay between the input and output. Now, a causal IIR filter cannot give a linear phase characteristics. Only an FIR filter exhibiting center symmetry in its impulse response can give the linear phase. Thank you all.